Welcome to the presentation on a deep meta model for environmental sound recognition. Myself Arun KS, associated with the Department of Computer Science and Engineering at Amal College of Engineering, Kerala. This is the outline of today's presentation. First of all, I will introduce what is environmental sound recognition. Then the motivation for the proposed work will be discussed. After that, related works will be presented in detail. Then the proposed deep meta model will be explained in detail. After that, the experimental evaluation of the proposed model will be presented and is followed by the conclusion. So first of all, introduction. So routine sounds, that means the sounds humans experience in day-to-day life except speech and music are commonly referred to as environmental sounds. So with the developing interest on query-based searching, such as content-based image retrieval or content-based video retrieval, the environmental sound recognition systems is nowadays instrumental in effective sound search applications. So in recent years, ESR is effectively incorporated in home surveillance, be it for helping old folks living alone in their house or for a smart house. Similarly, another application of environmental sound recognition can be the customization for the recognition of animals and poultry sound species by their distinctive sounds. In its early stage of development, ESR can very much identical to sound and music recognition models. Majority of these sound and music recognition models comprises of three main components. First of all, the signal pre-processing, then extraction of invariant features or distinctive features from these signals, and finally the developing a classification model to classify these sound signals to appropriate classes. However, these early frameworks are found to be inappropriate for environmental sound recognition because of its non-stationary behavior. So more recently, visual displays of audio signals such as spectrograms, which is obtained by different time frequency representations, can provide extensive description of the temporal and spectral structure of the original signal. In general, spectrogram is an efficient approach to visualize frequency spectrum of the underlying sound waves. The spectrogram images can be further analyzed using deep learning frameworks, and the hierarchical feature learning capacity of the deep learning frameworks can be utilized to develop more efficient and accurate sound classification systems, and it can also overcome these limitations of traditional approaches. So the motivation behind the proposed work: the lack of sufficient training data still hinders the performance of many deep learning models. An ensemble of deep learning classifier is often found to be much more accurate in such situations. So among the various ensemble models available in the literature, stacking, which involves the training of a meta model in order to aggregate the results obtained by multiple base level classifiers to generate the final prediction, is an efficient approach to combine the results obtained by various weak deep learning prediction models. So related works. Ahmad et al. Proposed a stacking based convolutional neural network model to recognize environmental sound. In this model, it takes time domain based features from the sound clips as their input, and they use a linear regression model to combine the outputs of three different weak CNN based architectures to yield the best accuracy in detecting environmental sounds. And later on, Rajab et al. And Liu et al. Used majority voting based frameworks to combine the outputs generated by four different base level classifiers to recognize environmental sounds. This model takes time frequency domain based features from the sound signals as their inputs. So all these two models assume only linear relationships among the classification scores generated by the weak base level classifiers. So From these existing works, it can be concluded that majority of these works employ time domain and time frequency domain features to combine the predictions generated by different classifiers. And moreover, spectrogram based features are not utilized in any of these existing approaches. Also, most of these ensemble models assumes a linear relationship between the prediction scores generated by base level models while ensembling is performed or stacking is performed. So these 5 CNN based architectures forms the base models in our proposed deep meta model architecture. So the original training set is used to train all these 5 models, and each of these 5 models will generate 5 different classification scores for the given input set. So after that, the original validation set will be provided, and from these, so we as I already mentioned, we are using 5-fold cross validation. So the given input data is divided into 5 folds, and corresponding to each of the 5 folds, all of these 5 base models will generate classification scores, and these classification scores are then fed as input to the proposed deep meta model architecture, and the final score generated by the proposed deep meta model for each of these 5 folds will be averaged to give final output. Different CNN based architectures, we need a mechanism to effectively aggregate the results yielded by each of these base level models to get a consensus final output. In stacking, a meta model is initially trained with the predictions obtained from the base level models as inputs and the expected target as the required output. So as a result, the meta model learns how to effectively combine the initial level predictions made by these level models. The deep meta model that aggregates the base level predictions is formulated as a deep neural network. A deep neural network with 5 hidden layers is trained with the above mentioned feature vectors to generate the final prediction score as the combination of the prediction scores given by the base level models. So given a set of all base level predictions and the target class level, the deep meta model can adjust the weights of the hidden layers such that it can learn a non-linear relationship between the base level predictions and their aggregate. So these are the experimental results obtained with the proposed deep meta model. Initially, the receiver operating characteristics for the proposed model will be in comparison with the three existing ensemble based methods such as Ahmad et al., Rajab et al., and Liu et al. Is presented for the first data set, and for the second data set the same comparison is also given. And then the comparison of the proposed deep meta model with the existing schemes on ESC50 dataset based on TPR, FPR, FNR and TNR values is presented in this table. So it can be seen that the proposed deep meta model outperforms all these existing 3 models. In case of TPR and TNR, it can be easily visible from these slides. TNR and FPR, and in all these evaluation metrics, the proposed deep meta model outperforms all the existing approaches. Moreover, it was evident that the proposed deep meta model was able to automatically encode the complex interrelationship between base level models and thus to entitle a superior prediction. That is, as we have already mentioned in the literature review part, that is in linear regression and all, we are not considering a non-linear relationship between the prediction scores generated by the base level models. But in this deep meta model framework, we are employing a deep neural network architecture, and it can encode the complex interrelationship, that is non-linear relationship among the base level models, and thus to entitle a superior prediction. So these are the major references. Okay, thank you.